And today you guys are going to learn about the Coulomb's law, ionization energy, and how they relate to the distribution of electrons in an atom.
Now, you guys probably already know that electrons are negatively charged particles that revolve around the nucleus.
I love you, nucleus.
I love you too, electron.
My world revolves around you.
But electrons aren't just randomly scattered around.
Actually, it's not random at all.
I think it's time we take an in-depth look at how electrons are configured in an atom.
Sounds good to me.
Electrons will repel other electrons, and protons will repel other protons. Meanwhile, electrons and protons are attracted to each other because of opposite charges. And according to Coulomb's law, the closer they are, the more they will attract to each other, and vice versa.
As you can see, the attractive force of magnets is greater as they get closer to each other. Charged particles work the same way. The closer they are, the more they attract. Additionally, the closer they are, the more they repel.
Now, Anik, time you learned about ionization energy. It is.
Isn't that the amount of energy it takes to remove an electron from an ion?
Very good. And because of Coulomb's law, the smaller the atom require, the higher the amount of energy it will.
And therefore, the greater the ionization energy?
And because each subshell adds a considerable amount to the atomic radius, a great difference in the ionization energy between atoms of different subshells there is going to be.
So how does this help me determine the distributions of electrons in an atom?
For each electron you remove, a corresponding ionization energy there is considerably greater than the second. If the first ionization energy is the jump down the subshells, there was.
What must I do now, Master Yoda?
Use this information to ace Dr. J's test. You must.
To start with, let's draw a nucleus. Now, let's add some electrons. Damn it, Jake! You see, you can't just throw electrons up there wherever. There has to be some order to it.
Oh shucks, I forgot about that.
That's where electron configurations come in. Okay, class, here's an easier way to show electron configuration. We'll start with copper, 29 electrons. Let's see if Jake can do it correctly. See, there's the first mistake. The off-broad principle states that electrons always go to the lowest energy level first, 1s. So that's where Jake's going to start. And Pauline's exclusion principle states that there can be no more than 2 electrons in any orbital at any time. And those electrons have opposite spin, shown by the opposite direction of arrows. Now, Hund's rule states that electrons always make sure that each orbital has 1 electron before they double up.
So I gotta fill all them up before?
Exactly. That's how you do it.
Whoa, hold up. Why is 4s before 3d?
Because on the periodic table,
In an atom, the electron cloud is separated into shells, subshells, and orbitals. Each shell corresponds to a period on the periodic table. An atom that has an electron residing in only the first shell is going to be found on the first row of the periodic table, either hydrogen or helium. An atom with electrons found in the first 4 shells is going to be found on the 4th row of the periodic table, and so on. Within the shells, electrons exist in the different subshells. There are 4 possible subshells: S, P, D, and F. The S subshell hold 2 electrons, 2 per orbital. P can hold 6, D10, and F14. In addition, the first shell contains only the S subshell, the second shell contains only the S and P subshell, the third shell contains S, P, and D, and the fourth contains all 4. This is shown on the periodic table, as the first row contains only 2 elements, only the S subshell. The second row contains 8, S and P. However, the third row also seemingly contains 8. Why? In fact, the transition metals actually represent the D subshell of the row before. But because they are further to the right on the periodic table than the 4s subshell, they are a higher energy.
That's how you do electron configurations.